Okay, I'm Steve Croft, and here with David Spergel, the winner of the 2018 Breakthrough Prize in Fundamental Physics. Thanks for joining us.
Pleasure.
What did you want to be when you were a kid?
This is embarrassing. When I was a kid, I wanted to be an astronomer. Showed very little imagination. I've actually done what I said I would do.
It's funny, that's the same for me as well. And what was this first science question that really fascinated you?
You know, I'm of the generation that watched Star Trek, and wondering whether there were aliens out there was certainly one of the first questions I wondered about.
And what's your opinion of that question today?
I still don't know. I think at this point, we astronomers have done a lot of the work we need to on this. We've shown that planets are common. I think from what we know, we suspect that there are indeed Earth-like planets out there. Now the question is really one of first biology. Given a planet that's like Earth, how often will life arise? And the next one is a question really of political science. Given an advanced life form, how long do they survive before they blow themselves up? Do they expand through the universe? Or is intelligence in some way self-destructive? And we don't know the answer to those questions at all.
Are you an optimist on those questions?
I'm generally an optimist, yeah.
So what was it that got you into your field of research?
I was fascinated by the question of how the universe began. Fascinated by general relativity. As an undergraduate, I took courses in general relativity and cosmology and thought that these were deep, profound questions. One of the things that, to me, is remarkable about the field I've been is there are a whole bunch of questions that we asked when I was a graduate student and undergraduate that we now know the answer to. And we've made real progress towards sort of a standard model of cosmology.
And what's it like being a theorist on a team of experimentalists?
Well, they don't let me touch anything. It was actually a lot of fun. Before working on WMAP, everything I did was sort of single author or papers with one or two people. They were short-term projects. And WMAP, in the end, turned out to be a roughly 20-year adventure. And we all got to know each other very well. As a theorist, I realized sort of my job was to figure out unusual things in the data. And one of the most important things to do that was I had to start to understand the experiment. So I ended up learning a lot about how the experiment works from my colleagues.
What was the most surprising thing about working on WMAP?
How simple the universe turned out to be. I mean, in a way, the surprising thing was there weren't strange things, that everything we see could be described by 5 basic numbers. We were able to measure 1 million independent points in the sky, and the basic picture that we saw fit in with all the other observations, and that we were able to construct this coherent picture of what's going on. I find it strange, actually, that the universe has properties that humans can understand. Why did evolution select us for this? Why did this happen? I don't know. I mean, this is certainly not the first to observe this, that the strange thing about the universe is its simplicity. But we really saw this in WMAP, because we made this map of the whole visible universe. We made this map where we were able to look at parts of the sky that had never been in contact before in our standard picture and see the same properties everywhere. And it is as if the universe decided to be as simple as it could be to produce what we observe. And to me, that was the great surprise.
And do you lie awake at night sort of wondering about the philosophical implications of this?
Yes, actually. I think while we've answered a whole bunch of questions that drove cosmology in the past, how old is the universe? What is it made of? What's its shape? What's its long-term fate? How do galaxies arise? We're left with a whole bunch of, I think, deeper questions Atoms, the stuff that make up us, make up only 5% of the universe. The remaining 95% is in the form of some new particle, dark matter, and what's energy associated with empty space, dark energy. While we have a kind of coherent picture of how you get from the fluctuations we see in the microwave sky that tell us what the universe looked like 400,000 years after the Big Bang to today, we don't really understand the physics of the very early universe. What drove this rapid expansion that produced the fluctuations we see? What was there before the Big Bang? These questions now, after our measurements, I think become more relevant because we're seeing the echoes of what happened in the first moments of the universe.
It's surprising to me when I took undergraduate astronomy, we didn't know the age of the universe within a factor of 2. The textbooks that I was reading said, it's somewhere in the 10 to 20 billion year range. And now your work has really kind of put precise numbers on that. We're in the era of precision cosmology, as it's been called.
Yeah, no, I think that was really the transformative thing that we did. We helped take cosmology from being this field where you knew the density of atoms to factor 10, the age of the universe to factor 2, how much matter there was in the universe to factor 3, to now we're measuring these things to 1% or 5%. And now worrying about discrepancies between one experiment and another at the fraction of a percent level, a couple percent level.
What's the most important measurement that we can make next, which will help transform our understanding of the universe again?
Well, the measurement that we're hoping to make, and this is to detect gravitational waves from the early universe. And because those gravitational waves would have been generated during the first moments of the expansion and give us insight into what's going on then.
Some people care about what the universe is and how it works, and others don't. Why should they care?
I think people care for 2 reasons. One, we want to understand. And the other, that our understanding the universe lets us control it better, right? The fact that particles can tunnel through quantum barriers was this fascinating bit of physics. It lies behind how transistors work. Mm-hmm. The way nuclei vibrate, it was sort of this obscure piece of physics. But if you need to get an MRI scan, you are really glad that some physicists in the 1930s and 40s and 50s were thinking about this. So there's lots of technological spin-offs of what we discover, and lots of spin-offs also of how we discover it. So astronomers looking to find the signal from neutron stars, their radial pulses. We're trying to figure out ways of handling interference. And that approach is the basis of Wi-Fi. Now, when I sell astronomy to someone who pays for it, the government pays, these are the reasons I tell them, is we get these benefits. This is not why I do it. Mm-hmm. I mean, I'm one of the people who does these things because I'm interested in the questions, how the universe began, what's out there. And I think it's one of the wonderful things we do as humans is understand the universe we live in.
Do you have more questions now than when you started?
Absolutely, yeah. I mean, I think the more you learn, the more you realize we don't understand so many basic things and that there's so many deep questions we don't know the answer to.